Good evening, everyone. My name's Rob Gell. Have the privilege of being the president of the Royal Society of Victoria, and it's my pleasure to welcome you all here tonight to the Royal Society of Victoria's Young Scientist Research Prizes competition for 2024. This is one of the highlights of our year, and we always love to see what young scientists are doing. Before we begin, we must acknowledge that all of us are located on the traditional lands of our continent's First Nations peoples. Here at the Royal Society of Victoria's historic headquarters, we're coming to you from Naarm, the lands and waters on which metropolitan Melbourne was established, on the country of the Wurundjeri and Bunurong peoples of the Kulin Nation. Never ceded, and I invite those joining us on YouTube tonight in live stream to acknowledge the traditional custodians of your own country and join me in paying respects to elders past and present, and likewise extend that respect to any Indigenous people who have joined us tonight for this meeting. I'd particularly like to welcome the many family and friends and PhD supervisors who've joined our members to support the finalists for this year's competition. This is one of the highlights of the Royal Society of Victoria's calendar, and certainly something that we look forward to with enthusiasm and anticipation every year. We have a great night ahead of us. I'm seen not deeply, but even just the topics of the 8 presentations we'll see tonight, I think you'll find very, very interesting. We'll be hearing from Victorian PhD graduates and learning about really the latest research emerging across the disciplines within our state's many research institutions. And as our 8 finalists were selected from a very highly competitive field of 42, we do have some truly high quality work to share with everyone this evening. Anyone who works or tries to work in research can tell you how intensely competitive and demanding the scientific profession is. There's a growing demand upon all scientists to not only conduct research, but present and publish the results to peers within disciplinary clusters and networks, but also to demonstrate their skill as a science communicator to non-scientific audiences. And that's largely what's going to happen tonight, which includes the governments and industries who stand to benefit from the fruits of their research endeavours. I might add that the private and public sectors are increasingly the most viable graduate destinations for our highly skilled postdoctoral workers. And I encourage anyone from industry or government in the audience tonight or online with us, whether, as I say, we're online or in the room, to reach out to these talented young people if you have any ideas for channeling their talents productively in years to come. We'd also like to hear from you about your future role and how you might work with us here at the Royal Society as we begin somewhat of a transformation, and including business and government in the work that we do. So this challenge for scientists to communicate to non-scientists means mastering the esoteric language and taxonomic base of your discipline, while also developing the ability to make this refined knowledge both accessible and engaging to make it clear in engaging language that both educates and persuades those who are unfamiliar with your specialised field of research. So, whilst our finalists here tonight, particularly, of course, due to the quality of their scientific work, they'll also be assessed by our judges on the clarity of their presentations for scientists and non-scientists alike, including their ability to respond to questions from our judges and, if time allows, from our audience members as well. So a warm thanks to many colleagues who are joining us tonight as judges, many of whom are also our assessors in singling out our finalists from this very wide field of 42. So a quick but heartfelt acknowledgement of all the excellent human beings who displayed on the screen. I think Mike put the names up. So thank you to all for your great assistance in both collecting our finalists, but also in your judging. So thanks so much for dedicating your time and energy to this year's competition. So this year we welcomed 2 new sponsors as well, which we're delighted to have, these being our supporting partner, Geoscience Australia. So a big shout out to Geoscience Australia and all our colleagues there. And our category sponsor for the first talks we're going to hear tonight, which is the physical science category, that being the Australian Radiation Protection and Nuclear Safety Agency, or APANSA. So to get us underway, I'd like to invite APANSA Senior Manager and Medical Physicist, Dr. Ivan Williams, a member of the Royal Society of Victoria for some time, to come up and say a few words about the agency and the diverse opportunities that Panza provides for early career scientists considering a postdoctoral career. I've also been told, Ivan, you actually did present here back in 2015. So welcome back to the microphone. Please welcome Dr. Ivan Williams.
Thank you, Rob, and thank you everyone for this opportunity. And I'd like to present apologies from Dr. Gillian Hirth, who is the CEO of ARPANSA, and she could not be here tonight. Now, I'll just talk a little bit about ARPANSA, the Australian Radiation Protection and Nuclear Safety Agency. How do we do that? We do that fundamentally by measurement. And when I look at the topics today that are being presented, it's really interesting because we measure in seawater, we measure in the air, we measure inside people, we measure inside biological systems, we measure in the dirt. And if you have a look at the categories today, pretty much all of them are looking at measurement, and they're also looking at modeling. We also do modeling. We model in the air, we model the water column, we model the biological systems, we model people, we model detectors, we model MRI machines and their interaction with electromagnetic fields and how that affects electron transport through human body and deposits dose. So we're all about radiation protection of people and the biological system and pretty much every facet of that. And so it's worth acknowledging that when we look again at the presentations today and people worrying about employment opportunities, we have employed about 40 people, new recruits, over the last 18 months, and well over half of them are in the physical sciences and in the mathematical sciences. And we also have a regulatory branch, which also does finite element modeling, engineering modeling to understand how materials behave under radiation fields and radiation insults and the long-term safety impacts and issues associated with that. So I just like to remind everybody that there are a lot of jobs in this space, and we're going to be recruiting, and we're based in Melbourne. So with that, thank you very much again. And I'd like to invite the new speaker.
I think that message has been well received, Ivan. Yeah, certainly. So thank you, and thanks indeed to ARPANSA for the excellent support you've provided this year to our early career scientists in this competition. So, as we mentioned, we have 8 presentations to attend to tonight, so you'll need to stay focused, stay alert, and I'm sure you'll enjoy them. They're all short, but they do certainly pack a punch and need to concentrate to keep up. This year we've selected the order of presentation by prize category. You don't have to know this really, but in reverse alphabetical order, followed by family name in alphabetical order. Has that been an issue in the past, Mike? Always an issue, okay. Well, you've got the drill. Each presentation will be 10 minutes, after which we'll have 5 minutes for a question and answer with our panel of judges for each finalist. And I think the judges are all squared away. You've got your note sheets and all the things that you need. And Mike, and if there's questions on YouTube, we'll have those as we go. Let's begin. So we have 2 presentations in the physical sciences. The first is Mr. Suraj Loomba. Where's Suraj? Come up as I introduce you so people can, good to meet you. Are you nervous yet? A little bit? That's okay. You'll get over it. Suraj is at RMIT University. His lead supervisor is Nasir Mahmood, and he's presenting tonight on the synthesis of scalable 2-dimensional materials for industrial scale electrochemical seawater splitting. Seawater, we've got the first, here we go. So go and talk to Ivan later.
Good evening, everyone. My name is Suraj Loomba, and I am from materials. Sorry, my bad. I'm from Materials for Energy and Environment Research Group at RMIT. The topic of my today's presentation is synthesis of scalable 2D materials for industrial scale electrochemical seawater splitting. So, excessive use of fossil fuels ever since the industrial revolution began, it has been a detrimental impact on the environment and also depletion of these important resources. ever since the last few decades, the climate crisis have been getting bad, and it's going to get worse for our future generations. It's not like we can make a mask for Earth like we used to wear during COVID or when we are sick, right? But so we need to look for alternative sources of energy, renewable sources of energy like wind, solar, and tidal have been on the rise. But because of their intermittency, they cannot entirely replace fossil fuels. In recent years, hydrogen has been viewed as a potential replacement to fossil fuels. However, commercially, about 96% of hydrogen is produced through burning of natural gas or syngas, and it has emissions, so it's not completely clean. And only 4% of hydrogen is produced by water electrolysis, and that has net zero emissions. Why? Because there are some challenges associated with water splitting. So first, water is a limited resource, especially fresh water. It's about 3% of Earth's total water reserves. And considering the increasing demand of hydrogen, it is expected that 20 billion meter cube of water will be required every year to meet the increasing hydrogen demands, which can actually put about 80% of the world's population under threat of water scarcity. So we need to look for resources that can actually replace fresh water as well. There are other disadvantages and challenges associated with freshwater, like the limited stabilities and working efficiencies of the currently commercial catalysts, like PTC or ruthenium or iridium dioxide. So other than that, they're very expensive as well. And right now, if you need to produce hydrogen, the cost is about $8 to $10 per kilogram of hydrogen. That's very high when you compare it with fossil fuels, which is around $1 to $2, maybe less per kilograms. Seawater, on the other hand, it's an abundant resource and amounts to about 97% of Earth's total water reserves. Especially if you see from this map, a lot of countries around the world, they have pretty good access to seawater as well. Seawater also have added advantage of tidal, solar, or wind energy on shores, which can be used to produce energy to split water molecules. So basically no emissions from this whatsoever. However, there are challenges with seawater as well, obviously. So first is the presence of ionic salt and microorganisms, which can actually corrode the catalyst and electrolyzers that are being currently used. The biggest challenge is chlorine evolution reaction, which is chlorine gas. Although chlorine is a value-added product, but considering hydrogen demand is going to increase, about 3 to 4 times more chlorine will be produced. And then there will be an issue of disposal of chlorine gas as well. So another challenge. Other than that, so right now, a lot of players, very big industries all around Australia, even all around the world, like Fortescue, Hysata, they are working on setting up different plants, like pre-treatment or desalination plants, so that they can remove all any ionic salts or any chlorine from the seawater. But not all small-scale industries or new startups have that kind of money that they can set up a new desalination or pre-treatment plants. So alternative sources need to be found. The next, so what I have done is, like, our group, we have worked on developing catalysts that can be used for seawater splitting. Other task is to develop electrolyzers as well, but my focus have mainly been on developing catalysts for seawater splitting. Throughout my PhD, I have developed catalysts for seawater splitting, and I have actually gotten a lot of media attention thanks to our MIT. And we have been approached by numerous industries to work on the commercialization of these technologies as well. And we hope that in coming years, we will be reaching the government target of $2 kilogram of hydrogen per kg. Sorry, $2 per kilogram of hydrogen. So next, I'll take you through my research. So I have used a very easy high temperature pressure synthesis route that's called hydrothermal. So we have developed a material which looks like this, very thin, highly porous. So what it does is it helps in enhancing the splitting of water molecule into hydrogen and oxygen. As a result, a catalyst was able to perform better than the commercial PTC catalyst in seawater, and which was about twice as better than PTC. Additionally, it was able to run for about 100 hours in alkaline seawater. PTC, on the other hand, can run about like 3-4 hours. So basically 10 times better stability performance than PTC. Based on this, we employed it for full water splitting, using it as a full cell both on cathodic and anodic side. And our catalyst performed better than the commercial PTC and iridium oxide catalyst. And when tested for stability, it ran for about 33 days without any performance degradation. So what we learned from this was, although our performance was really good, but when it came to industrial applications, we were still lagging behind. So we realized that more focus needs to be on the anodic side. That's for oxygen evolution reaction catalyst. So next we developed, focus on developing catalysts for ampere level chlorine-free anodic seawater reactions. Like I told you earlier, seawater competes with anodic oxygen evolution reaction. So catalyst has to be developed, which can perform at industrial scale, but can also avoid chlorine generation using seawater. So what we did was we took two different catalysts, which has two distinct advantages, brought them together, grow one on top of the other, as you can see from figure B over there. These two catalysts had unique properties, combining both their advantages and no common disadvantages, and having strong bonding between them. As a result, the catalyst was able to achieve a current density of 2 ampere under a potential of 2 volt, which was 10 times better than iridium oxide catalyst. Interestingly, it's 65% cheaper as well. And when tested for stability, it was able to run continuously for 45 days without any performance losses. We also did a stability test at a potential at a current density of about 1.5 ampere. That's 3 times the current industry demands. And we ran that for about 4 to 5 days without any current losses. So we also did another simulation testing over here. So like I talked about using renewable resources for energy generation. If you use renewable sources, they can be intermittent. And when you're in industrial applications, there can be shutdowns as well. So during that time, there might be instances that you might have to left the catalyst in seawater. And seawater being corroded, if the potential is not being applied, it can foul the catalyst, even destroy it. So what we did was we left our catalyst that was run for 1,000 hours in the setup for like 5 days. And after that, we restarted it again with 90% current efficiency. So although our catalyst performed exceptionally well, we have to make sure that there was no chlorine generation. So these experiments were done to ensure that there was no chlorine gas generation or no hypochlorite as well in the seawater. So we have successfully developed catalysts for oxygen evolution reaction at ampere level with current densities far greater than iridium oxide, and have made sure that there was no chlorine evolution as well. So to summarize, we have developed catalysts for green hydrogen production by direct seawater splitting. Our catalyst for HER performed twice as better as PTC. And for OER, it was 10 times as better than iridium oxide. And it's 65% more economical than current commercially used catalyst. Well, moving on towards industrial collaboration, there's already an ongoing pilot scale testing in India on one of my patented material. And moving on towards the other patented technologies, RMIT is in talks with one of the Australian companies to set up a plant for commercialization. I think they're first planning to set up a pilot plant within RMIT and then move on from there after the pilot scale testing has been done. In the end, I would like to acknowledge my supervisor, Dr. Nasir Mahmood, and my research group and colleagues, RMIT University facilities, and Australian Synchrotron for all the help that I have gotten through my 3.5 years of PhD. Thank you for listening.
Some time for questions, firstly from our judges.
Thanks, Suraj. That's so fascinating. I'm going to ask a dumb question. Why don't we want any chlorine?
Like I told you, chlorine is a value-added product, right? But if we produce hydrogen, that's going to be a lot of hydrogen. It can produce 3 to 4 times more chlorine than we require in a year. And 3 to 4 times chlorine, it's a lot, and chlorine can be poisonous as well. So we don't want excess chlorine. Otherwise, like I said, there will be another issue. We have to look ways to dispose of chlorine as well. Thank you.
This is really cool, and you've said that it's 65% more economical compared to current commercial catalysts. Is that translatable? Like, if you scale this up, will that cost still be the same?
So this has been done, I think, based on 1 kilograms of catalyst requirements. So we haven't done on a large scale, but considering 1 kilograms in labs, we normally produce in milligrams, like 50, hundreds. So we have done these calculations. Hopefully this will be published within a month or so. I'm just finalizing this work as well. But yeah, it's based on 1 kilogram of catalyst requirements. I hope that answers it. Thank you.
Thank you. That was really interesting. I have a question about the second catalyst that you developed.
Yep.
Where you fused to other catalysts.
Yep.
So 2-part question. Do you know where the catalyst behavior is happening in the junction zone or in the two materials on either side?
Yeah.
And the second point is, was this your first attempt at combining catalysts, and did you predict it?
So yeah, the first question. So these are basically called 2D heterostructures. So we have used liquid interfacial strategy to grow this material on top of the other. And what are DFT calculations, like theoretical calculations, they have shown that most of the work is happening at the interface, as a result of which basically one is cobalt MOF, the other one is tungsten oxide borate. So it is boron as well. So there's tungsten as well, and then cobalt as well. So what they are doing is cobalt MOF is bonded to tungsten borate via ionic bonding. So that ionic bonding is actually really crucial in providing its stability when using it seawater, especially most of the work they have been done, it's using 1 molar. We have worked it on 6 molar. So that's industrial applications. 1 molar, it's still not that corrosive, but if you add more potassium hydroxide, it gets more corrosive. So this helps it, and it actually wasn't. So I tried other strategies as well, but it requires a lot of literature review and all that. I think I read about 10, 15 journals before I came to this conclusion. It didn't work in the first instance as well. We had the morphology, but not the exact performance. So we had to tweak some things to get it here. But and it's not only just one material. So we have actually synthesized it with different materials as well, and with all very similar and ampere level performances as well. I hope that answers it. Thank you. Any other question?
General audience questions. Anything from online, Mike? Oh, hang on, so Jane.
Suresh, that's fascinating. And I can hope for a future where we've got green hydrogen or industrial applications. I would see a future where there's application to the likes of our big mining investors who are very keen to develop this, and our steel producers. So hopefully there's a future source of funding for you there. So I'm looking forward to hearing much more about this work.
We hope so. We actually are developing another technology where we can capture carbon dioxide as well, through all of the system. I can't talk about it, but
Yep, go for it.
Thank you. Okay, perfect.
Good. Suraj, thank you.
Thank you so much. Thank you.
Suraj, last night I went to the launch. Ever heard of a bloke called Garneau? He's written another book called let's tax carbon. And there's a bit of stuff about hydrogen in it, so it's probably worth a bit of a read for you, so I can recommend it. Now to our next presentation in the physical sciences. Here's Mr. Bennet Sam Thomas. Where's I met him earlier. He's from Monash University. His lead supervisor is Professor Sankar Bhattacharya, and his presentation tonight, welcome. His presentation tonight, extraction and separation of rare earth elements from Victorian brown coal fly ash. It would be really good if we could do something with brown coal fly ash, wouldn't it? Yeah.
Perfect. All right. Good evening, ladies and gentlemen. It's an absolute pleasure to be here tonight. As I've been introduced, I am Bennet Thomas, and I am a final year PhD candidate at Monash University. Tonight, I will be giving you a talk on the title, Extraction and Separation of Rare Earth Elements from Victorian Brown Coal Fly Ash. It's quite a mouthful, and I have the pleasure of sharing this research with my two wonderful supervisors, Professors Shankar Bhattacharya and Ramit Singh. So I'm going to sort of segue from where we ended. Yeah, fascinating stuff. We love, I mean, it inspires me to see how we are pushing the frontiers of science and engineering to get new fuel source. But this iconic image right there, I know many of you can relate to it. There was a message that was given out back in 2017 that coal is still needed. But here I am trying to play devil's advocate here and say there are two problems with using coal. One, it's not green. We need greener sources of fuel. And two, there is a waste problem. And tonight I'm going to draw your attention towards that. Now, here's the deal. 70% of electricity for Australian households come from burning coal. Now, that means we generate nearly 11.4 million tons of coal ash every single year. That is a problem. So you might be wondering what is coal combustion byproducts? And a simple example is when you burn wood, you get wood ash. When you burn coal, you get coal ash. However, in a power station, what happens is coal, based on its density and weight, some of it flies away. And what we collect, about 80 to 90%, is known as coal fly ash, right? And that's the major constituent of coal ash right now we are focusing on. So what's the theme of my talk is to clean up our act. We have a duty of care to do this, not just for ourselves and our future generations, but for what we have messed up so far. The problem, we have no commercial application so far for brown coal fly ash, either in civil or construction projects. Two, it is disposed of in ash ponds, raising severe environmental concerns. So we started talking about this. We started analyzing the problem. We are like, why isn't this being used? Why isn't there an application for coal fly ash? Here's the deal. You could possibly substitute cement for concrete and use fly ash, but that's bad for business. People don't want to do it. So what else could we do with it? That's where we came in with a different dimension of thought, and we said, what if we could extract valuable metals from coal fly ash? And here we are in the second decade. Enter rare earth elements into the chat. So what are rare earth elements? They're a group of 15 lanthanides, as you can see in the modern periodic date table, and including scandium and yttrium. These, do not let the name fool you. These metals are not so rare and are in fact present all around us. But here's the deal. They are difficult to mine from ground up because there are very limited mining locations that we can actually do a feasible and a commercially important process for mining rare earths. So the question is, what's the big deal, Ben? Why are we talking about rare earths? Here's the thing. If you walked in tonight with a smartphone watching us online from your computer screens or televisions, you're using something that uses rare earth elements. We need it. Have you ever seen a big line outside Chatty when a new iPhone drops? Yeah, we need all these gadgets and we are a consumer market. Now, Australia being blessed with some really good resources, here's another problem. We are good at mining, but we do not refine it. We do not process it. Neither do we make anything out of the metals we mine. We send it out to countries where environmental rules are a bit more laxed. So we took on this head on. We asked a few important questions, which is, can we utilize a feedstock which has already been mined, washed and processed and as a secondary source of rare earth elements? Is it possible to do it from brown coal fly ash? And if so, how do they exist? And finally, can we do it sustainably so that we can build opportunities in Australia and create more manufacturing industries right here, right now? So what did we do? We collected samples from 3 power stations in the Gippsland Basin, Yallourn, Morwell, and Loyang. One of that is shut down, and both of them have imminent closure dates. So we fell on some prior art, and we saw that Bone and Sharp in 1981 observed trace elements of rare earth elements in Victorian brown coal. Now, this is way before I walked on the face of Earth. Now, 40 years later, it was for the first time, we understood that there were all 17 rare earths present in Victorian brown coal fly ash. Now, what that means is we just weren't looking right. We had to just look at a waste or something that has been discarded to see that it was nearly enriched 200 times in brown coal fly ash. How fascinating, right? So the question then was, is it really important? Is it viable? Can we commercialize this? What is the impact of this research that we are doing? So another important finding that we did is Loyang Power Station, which is still in operation, had one of the highest concentrations of rare earth elements, around 400 parts per million. Now, that is important finding for us because it is still in operation, still generating fly ash, and we can still use it. So we dived in deeper. We wanted to understand. Now, these beautiful images were collected from a scanning electron microscope, but after hours and hours of scan, I can promise you tonight that we found nothing. But we did build the first piece of the puzzle. In our recurring scans, we saw that aluminum, silicon, titanium, and iron kept coming up in our energy scans. So the question was, where are these rare earths? I mean, we see everything. We see the bulk metals. We're seeing what we're not seeing what we're looking for, but we're seeing everything else. We started asking questions, are they present in some sort of rare earth bearing mineral forms? And from an X-ray diffraction study, we realized that most of the mineral content in Loyang, which had the highest rare earth concentration, was mainly quartz. Now, here's the deal. Quartz cannot hold rare earths. So there goes again our hypothesis. And we had to come up with the next hypothesis that, okay, they're not present as crystals, so maybe amorphous structures, right? So what we did is we went along with a counterintuitive approach. We did sequential extraction using 6 different solvents. We mixed it with water, mildly acidic. It is classical hydrometallurgical techniques that we employed. However, here's the deal. We found that nearly 60% of it were in fact present in amorphous structures. So from an engineering mind and engineering perspective, here's what we find. Here's what we concluded. If we were to actually target these aluminosilicate structures, which is hard to dissolve, we could effectively get more than 80% of rare earth elements from coal fly ash. But we were not satisfied. We were like, we just need to figure out how they look like in fly ash, or is it really there? I need to see a visual evidence. That's when we went and knocked doors with our friendly Australian synchrotron neighbors. And what you're seeing here, ladies and gentlemen, for the first time after a couple of years, we saw rare earth elements. Now, these tiny specks in a beautiful black canvas, those are rare earth elements, literal definition of needles in a haystack, right? And what we wanted to conclude was, how did they exist? What did they look like? So it's a couple of scans and numerous scans, in fact, we see that they were present as oxides and some of the elements coexisted as well. So here's another question. Was it actually in amorphous aluminosilicate structures? So here's something we found as well, that after the samples were partially processed, there was no oxides, and in fact, they were present in glassy structures. And there comes in my final bit of the research to show you that we were able to extract nearly 55% using just organic acids. Now, that's not good enough. When you keep it against an inorganic or toxic chemical, that's just not great. So what did we do? We used ultrasound high energy pulses of ultrasound to break into these hard structures. And ladies and gentlemen, we did achieve 99% extraction efficiency. That is even better than some of the inorganic acid processes that's out there. So is it scalable? We tested, we started with 100 liters, we scaled it up to 30 liters, and the results are reproducible. And the final bit of the research that we did was to separate them out. And here you go, some beautiful looking crystals and rare earths finally separated using electrodielectric separation techniques. And today, as I speak, we have about 40 to 60% rare earth separations achieved in our lab, and we're targeting to push that to 90%. Yeah, so what's the impact and significance? This research is not just for coal fly ash. We can translate this to mine tailings, recycling electronic waste. We are at a future we need to recycle and preserve and conserve the resources we have because these resources are finite. And on that note, I'm just going to conclude and say a shout out to these following people without whom we couldn't have done this research. And yeah, the floor is now open for questions.
I actually work with a company that uses not Victorian fly ash, but Hunter Valley fly ash and imported fly ash in cement as a cement replacement to replace the embodied energy. This is a lot more valuable. It's not a very high value use, is it? Questions? There's one at the back. Oh, Richard.
Yeah. Hi, Sam. Thank you for that. Great storytelling. Great. But really brought that to life. I did read your paper actually, and I had a couple of questions. And one was around what struck me as the very different concentrations depending on which mine you're talking about. How was the sampling done? So was it representative of the entire tailings, or is it just part of the?
Yeah,
you know, is it,
great question. Yeah. So what we did was we took up different parts of the sample. So we collected them in 20-liter pail containers, and sampling was done across 10 samples from different portions of that bucket, and averaged out over that. So it is not just one small fraction of the coal fly ash that we collected. Instead, it was multiple samples sent across 2 different labs and also done with the classical HF digestion method. Yeah.
Fabulous. And how do these sort of concentrations compare with, say, other sources of these minerals around the world?
Yeah, great. So yeah, I probably should have mentioned this, is we're not trying to eliminate rare earth minerals, right? We need them. We're trying to complement what's already there. And in comparison, I would say if coal fly ash with Victorian brown coal fly ash around 400, I observed that Sydney Collie Basin has around 500 to 600 parts per million. Mineral ores, some of them can go as high as 1000 ppm and higher. So that's the relative standard that we're looking at. But I think the message that I would still push for here is that it's waste management and creating wealth from a waste source.
And then I'll...
Thank you for that presentation. In terms of scalability, I know you mentioned you used sort of different variants of I think it was 33 liters at the end you used to refine. In terms of scalability and mass producing this, so from a commercial perspective, what do you think are some of the sort of roadblocks that you might have to overcome?
Yep, great question. So we are actually working with a couple of companies already to scale this. Now, one of the roadblocks I probably would anticipate is the variability in the samples that we're working with. Now, my results are solid with coal fly ash, and we also tested with mine tailings as well. 2 is the sort of the funding landscape that we're working here as well. Whilst these results are promising, we need companies to come on board and work with us and say, hey, we want to bring this back to life. So to answer that question, 1 is sample variability, and 2 is the funding landscape we currently have.
Thank you, Bennett. That was a great presentation. So you mentioned at the start of your talk that there's this issue with what to do with all this fly ash, and you're taking these potentially precious metals out of there, these rare earth metals, but how much ash are you still left with, and how much have you reduced that ash by extracting those metals?
Yep, fantastic question. It's something we actually thought about as well. So I'm going to probably put this as this is phase one of waste management, right? There is still ash left behind. Now, here's the beauty. When you use organic, environmentally benign organic acid, a lot of that aluminum and silicon is still left behind in that structure, right? A possible usage of that, let's say the residue, is to make zeolites out of it. Now, that's, again, something we need in the industry. Catalyst, adsorbents, right? So that would be a part of our future research to actually get the residual bits and pieces of what we're getting back. So even at 55% at the starting, all that aluminum silicon can be converted to zeolites. So I think that should be the focus and the path that we're looking forward in the coming year, I would say. Yeah, thank you.
Yeah, thank you. That was a fantastic talk. This might be a silly question, but looking to commercialize this waste resource, would and if that is eventually successful, could that potentially breathe life into the coal industry?
See, I'm going to be a pragmatic here and say that's not the goal of this research, right? The goal of this research is to clean up the mess that we have created. So the intention is not to breathe or bring back coal, is to rather clean up what we have already created. And that's a lot, right? More than 100 years of coal burning that we had since 1919, at least in Victoria. We have a lot of coal ash that's already generated. Now, mining, that still happens. So the question comes, is this research translatable across from coal fly ash to mine tailings? And the answer is yes. So that's what our focus would be with the industries as well.
Ben, love the presentation.
Thank you.
I was looking at the power stations and when their shutdown dates are.
Yep.
It says Yallourn is in 2028, Loy Yang A is 2035, Loy Yang B is 2047.
Yeah.
And by 2038, most of the sort of things will be shut down. It takes a while to get this into commercial use. I mean, your work is incredible. Have you thought about any alternate ways of using this research? Because I guess the second question is, how much of ash is lying around in holes in the ground somewhere that we can retrospectively go back and get the rare earth minerals out of there?
Sure. Yeah, great question. So first, answering the first question, have you thought about translating this research? So once we reached the conditions of optimum conditions that we believe was, we tested with electronic waste, right? Recycling electronic waste. We got sampling from gold mine tailings, Western Australian gold mine tailings. We also sampled that, and we saw that with the ultrasound-assisted hydrometallurgical extraction, we could extract these rare earth metals. So it is not just coal fly ash, it is actually translatable across different domains. Now, answering question number 2, which is imminent closures and how much of fly ash is actually there. It would be hard for me to say how much in quantity-wise, but in conversations, we had a site visit to Loy Yang Station a couple of months ago, and we spoke with the engineers there and asked them, what do you do with all this ash? And they said, we just make a slurry and leave it in an ash pond, right? So can we collect and retrieve it? 100%. But putting a figure on that would be a bit hard at this stage, yeah. Awesome. Yeah, a lot. Yep.
Any other questions? Okay. Thank you, Sam. That's great. Well done. Yeah. We now move on to 2 presentations in the earth sciences, get that right. Miss Calla Gould-Whaley, where's Calla? Come up, say hello. Hi, good to meet you. Thank you. Great. Calla's from the University of Melbourne. Her lead supervisor is Professor Russell Drysdale. Her presentation, Extreme Southward Displacement of the Australian Monsoon During the Abrupt Climate Events of the Last Glacial. Phenomenal. Off you go.
Hi, everyone. So I'm going to be talking to you about the work that I've been doing with my really awesome supervisors to reconstruct Australia's climate over the past 100,000 years. So this seems like a long time ago, but it actually has some applications for the way we approach our current climate crisis. So I'm going to be talking to you about the arid zone. So this is a photo from Adnyamatnya country in South Australia, which is in the arid zone. So 70% of Australia is classified as either arid or semi-arid. And in these regions, evaporation is really high and there's typically pretty limited rainfall. So surface water is really hard to come by. So in these regions, we tend to rely on groundwater resources. So here is just a map of groundwater dependence in Australia. So with the light orange areas is where we use more groundwater than surface water. And then the dark orange is where we have complete or near complete dependence on groundwater resources. So you can see in a lot of regions in Australia, we're really dependent on groundwater. But the problem we have is that in a lot of Australia, groundwater recharge rates are currently really low. So we have a situation where across lots of Australia, we have more groundwater extraction than we do have recharge to the groundwater systems. And so a lot of the water that we're actually using is fossil water that entered the groundwater systems a long time ago, but isn't being replenished as quickly as it's being used. So if we want to inform long-term effective groundwater management strategies, we need to know a bit more about the conditions under which these aquifers were originally charged with water. How can we answer this question? Well, with something I'm very passionate about, speleothems. So not everyone may have heard of these, but if you've been to a cave and seen the stalactites and stalagmites, they're speleothems. So they're sedimentary carbonate deposits that grow in limestone caves. And they require infiltration of water through the soil and the bedrock and into the cave to be able to grow, which means they're a really good indicator of groundwater infiltration. So this is our study site, Mares Cave on Adyamatnya country, and it's sort of on the boundary between the arid zone and the semi-arid zone. And it contains these really interesting formations. So today it's way too dry for any of the formations to be growing, but the fact that they're present in the cave tells us that at some point in the past, the region was receiving a lot more groundwater infiltration than it is today. So these are quite unique formations called pendulites. So they begin as stalactites hanging from the ceiling of the cave with a downwards direction of growth. Then at some point, there's an increase in water infiltration, which causes the water table to rise and flood the cave so that the stalactite is submerged in groundwater. From that point forward, calcite is precipitated subaqueously on the existing stalactite surface. So this subaqueously deposited material has a radial growth direction. Then at some point, there's a decrease in groundwater recharge, which causes the water table to drop below the cave and there to be a hiatus in subaqueous speleothem growth. So because of this really unique and really interesting growth mechanism, when we see phases of subaqueous growth, this is evidence that there was cave flooding at the time because of higher water table, because of more groundwater recharge. And then when we see hiatuses in subaqueous speleothem growth is evidence that there was no cave flooding because there was a lower water table because there was less groundwater recharge. So they're a really useful archive for reconstructing groundwater recharge trends. So these are the three speleothems that we've worked on so far, MC 1901, 2001, and 2002. And you can see it's highlighted in blue, they all have that internal stalactite component, and it has that downwards direction of growth. And then they have this external subaqueously deposited material that has a radial growth direction. So if we're able to know the age of this subaqueous material, then we'll know when the water table was high enough to flood the cave and when the region was experiencing more groundwater recharge than it is today. But how do we determine the age of this material? Well, we use uranium-thorium dating. So uranium-238 decays to uranium-234, which in turn decays to thorium-230. And uranium-238 and 234 are incorporated in the speleothem in trace amounts as it grows, and they decay at a known rate. So we just have to measure their ratios in the speleothem material using a mass spectrometer like this, inductively coupled plasma multi-collector. And then we plug the results into this equation and we solve the equation to find the age of the subaqueous material. So we've done this over and over and over, and it's taken a long time, but we've accumulated this data set that shows us phases of subaqueous speleothem growth. So we have MC 1901 at the top, which sits highest in the cave. So it's only flooded by the most extreme cave flooding events. Then MC 2001, which is somewhere in the middle, and then MC 2002, which sits lowest in the cave. So it's going to be inundated by even relatively minor cave flooding events. So you can see our first phase of subaqueous speleothem growth occurred between about 100 and 88,000 years ago. and then the next between about 73 and 63,000 years ago. And then our longest phase of subaqueous speleothem growth occurred between about 58 and 39,000 years ago. And then since then, we've had relatively minor, short-lived cave flooding events. So we compared our results to incoming solar radiation in summer in the Southern Hemisphere. And incoming solar radiation, because we're lazy, just gets shortened to insolation. So we can see that there's a tendency for subaqueous speleothem growth phases to occur when summer insolation is high in the Southern Hemisphere. So this relationship indicates that potentially subaqueous speleothem growth and groundwater recharge at the site is responsive to tropical rainfall delivery. So I'll quickly try and run through an explanation of this. But if you think about the Earth receiving insolation from the sun, more insolation is received at the equator. So this creates a zone of warming and evaporation. So we have rising water-laden air masses, low pressure, cloud formation, and rainfall. So this is our monsoon region. So in Northern Hemisphere summer, when the Northern Hemisphere is tilted towards the sun, we have the monsoon system sitting north of the equator. And then in Southern Hemisphere summer, when we have the Southern Hemisphere tilted towards the sun, then all of these monsoon systems move into the Southern Hemisphere. So going back to our results, that's why when we see these peaks in Southern Hemisphere summer insolation, we can interpret this as evidence that the monsoon belt would have been sitting further south. And so we have enhanced tropical rainfall delivery across to Southern Australia, more groundwater recharge, and subsequent growth of our subaqueous speleothems. So it's not just insolation that drives the position of the monsoon belt. I wish it were that simple, but it's a really complicated system. But you can sort of summarize it in that the position of the monsoon belt is somewhat determined by the energy balance between the two hemispheres. So if you have warming in one hemisphere relative to the other, the monsoon belt is going to shift towards the warmer hemisphere. Lucky for us, speleothems can tell us about more than just growth phases. We can also get high resolution records of groundwater recharge intensity as well. So if we go back to our results and we're going to zoom in on this longest phase of subaqueous speleothem growth, and we have some extra results here. So at the top, we have speleothem growth rates, where an increase in speleothem growth rate indicates wetter conditions and more infiltration of water. So you can see we have these two pulses where we have an increase in the growth rates and so increase in infiltration. Below that, we have speleothem uranium isotopes, where an increase is also indicative of wetter conditions. So we also have these two periods of increasing, showing us that there was more groundwater recharge at the time. And then below that, we have oxygen isotopes from the Greenland ice core record, where an increase indicates warming in the Arctic and then a decrease indicates cooling. So you can see that our two phases of increased groundwater recharge occur while we have cooling in the Arctic. So we can see that when the Northern Hemisphere cools and the Southern Hemisphere is comparatively warmer, then the monsoon belt is drawn further south and we have more tropical rainfall delivery across Australia. So to summarize everything I've gone through so far, most of Australia is arid, and in arid regions, surface water is scarce and we tend to rely on groundwater. In some areas, we're completely dependent on groundwater for industry, for food production, and for drinking water. But in a lot of Australia, the amount of groundwater that we're extracting is actually greater than the amount that is being replenished in the aquifers. So a lot of the water that we're using is fossil water. So speleothems, fortunately, can provide us some insight into the history of the recharge of these aquifers, including the timing of groundwater recharge events and the intensity of groundwater recharge. Our speleothems from Southern Australia show us that aquifer recharge occurred thousands of years ago when Australia's climate system looked very different to what it does today, and when it received a lot more tropical rainfall than it does in the present. So the speleothem growth rates and uranium isotopes reveal that groundwater recharge intensity increased in response to Arctic cooling, which is unlikely to occur anytime soon. And this drew the monsoon further south and intensified tropical rainfall delivery to Southern Australia. So the takeaway message that I'd like to impart on everyone is that groundwater recharge in southern Australia occurred when the Earth's climate system was really different to what it is today. And as anthropogenic climate change proceeds, we could experience even less groundwater recharge than we see now. So if we want to prevent depletion of our groundwater reservoirs, we need to be managing them really wisely. And that's it.
Questions for Calla? Bill Birch. Sorry, Duke, all right.
Thanks for a fascinating presentation. Really appreciate that. You presented a phenomenal amount of information there, and I may have missed it, but I'm curious, what is the dating extreme using the technique that you are using? Because I know the oldest period was 100,000, I believe. And also, what was the sample size? Because yes, how many have you got in there?
Yes. Okay, so do you mean the extremes of the method? So the method itself can go back, I think, like some people are pushing it to like 600, 700,000, but it kind of cuts off. You have like increases in your uncertainties. And then there's other uranium-based methods. So you can go to uranium lead after that. But yeah, that's a whole different ballgame. Yeah. And in terms of the sample size of our actual data, that is a good question. I can't remember the exact number. A lot is the answer. I think it would be somewhere around like 200 dates. Yeah, which, I mean, it's a pretty expensive method, and we do column chemistry, which is very, very slow. So yeah, yeah.
Thanks, Calla. Nice talk. Your method was on one cave system, I assume. How reproducible is it if you go to another cave system, say a couple of 100 k's away?
Yeah,
maybe roughly the same latitude, but perhaps the same environmental conditions.
Yeah, totally. So it's a really good question. I guess the limiting factor is these subaqueous speleothems, they don't occur everywhere. So it's pretty hard to actually find somewhere where we can compare the results. And they're also limited by the occurrence of lime or carbonate bedrocks. So, if there's no carbonate, we can wish as hard as we can, but yeah. I guess to answer to how applicable it is, it kind of depends on the climate modeling side of things. So we're working with some climate modelers who, are kind of testing the physical viability of our method of increased, our theory of increased tropical moisture delivery. So if it is that sort of climate signal that we're seeing, then potentially, you're going to have tropical rainfall that's coming all the way from Northern Australia through Central Australia and to South Australia. So they could be slightly different groundwater systems, but if they're all receiving rainfall, they're all going to be recharging. They may be recharging at different rates depending on porosity and permeability, but they're all going to be moving in the right direction, more or less. So yeah, it is very aquifer dependent, but we kind of just have to be opportunistic and,
Thanks, Calla. That was a really great presentation. This is obviously not the topic of your research, but I guess I'm just interested in how your findings are impacting water policy.
Yeah.
So there's a lot of water being taken out of the ground, and there's plans to take a whole lot more. Your predictions are saying that maybe we're going to have less water because of the impact on the monsoon. And I know the monsoon is notoriously hard to model. If you look at climate change predictions, temperature were pretty good, rainfall not so much. Can you speak to that a little bit?
Yeah, so to be honest, when we first got these results, because of how far south our cave site is sitting, and we saw this kind of relationship with, insulation, we're like, there's got to be some explanation for, we were pretty skeptical that it would be this tropical rainfall coming down. And which is why we went to the climate modelers and said, is this physically possible? And from the results that we're seeing so far, yes, we could have more tropical moisture making it further south. It's also thinking about in this period of time, evaporation was so much lower that you have water and you're just not losing it as much. Yeah. So I guess I feel like I think I'm a small cog in the system. I'm not going to be able to say you'll get this much rainfall, prepare for this. I think it's more, yeah, I guess contextualizing the system, raising awareness about the fact that we are using really ancient groundwater in a lot of places. And just, I think sometimes hearing those big numbers, like 100,000 years, can really contextualize the idea that, you know, it is a limited resource to some extent. Yeah. So yeah, there's a lot more people though who are working on shorter timescales. At the University of New South Wales, they've got a really awesome project starting on that to monitor groundwater recharge, drip rate coming through caves. So I think that's where the most policy and application work lies. Yeah.
I think we need to wrap up our questions. Is that right, Mike? We've had our 5 minutes. Calla, thank you. That was fascinating. Our second Earth Sciences presentation comes from Venicius Vack Salazar. How'd they go?
Perfect.
Oh, okay, good. Cool. That was my only test for tonight. You've got one coming up. He's at the University of Melbourne. His supervisor is Professor Kim-Ann Lecau, and he's presenting tonight on the metagenomic and oceanographic data integration that reveals restructuring a global phycoplankton biogeography under climate change. So another climate project. Okay.
Good evening, everyone. Pleasure to be here. So today I'll be talking about the link between biology and the environment. I work professionally as a bioinformatician, but I still very much consider myself an oceanographer at heart. So I'd like to start talking about the Earth's biological engine. And I bet many of you growing up may have heard the phrase that the Amazon forest is the lung of the Earth. And don't get me wrong, the Amazon and other tropical rainforests are precious and they must be protected. But the real lungs of the Earth are the oceans. The oceans are essentially Earth's biological engine, and much of its power lies within its tiniest organisms, microbes, particularly phycoplankton, the bacterial and archaeal portion of planktonic organisms. These tiny organisms are fundamental to all life on Earth, driving key processes such as carbon cycling and nutrient dynamics. So they are driver of global biochemical cycles, and phytoplankton alone are responsible for at least half of the planet's primary productivity. So they're the base of the marine food web, supporting larger organisms such as fish and whales. But beyond the role in food webs, phytoplankton also play a crucial role in regulating our climate by absorbing carbon dioxide and contributing to global carbon sequestration. Essentially, they are the engines behind many of the biological processes that keep our planet ecosystems in balance. As climate change accelerates, understanding how phytoplankton communities are being affected is critical to predicting broader changes in marine ecosystems and in global biogeochemical cycles. And while we often think of life in terms of plants and animals, the reality is that the vast majority of life on Earth is microbial. What's even more remarkable is that much of this microbial diversity remains uncultivated. We've only scratched the surface of the microbial world. So the unseen majority is what we call these uncultivated microbes, which we can't grow in a lab, but they're thriving in every corner of the planet, particularly in the ocean. These microbes, including phytoplankton, are key players in Earth's ecosystems, yet most remain poorly understood. However, with advancements in DNA sequencing technologies, we now have a new way to explore this hidden diversity, which is the technique of metagenomics, which allows us to reconstruct microbial genomes without having the need to cultivate them. So metagenomics is a tool that allows us to study the genetic material of entire microbial communities directly from environmental samples, bypassing cultivation. Imagine trying to solve the world's biggest jigsaw puzzle, where the pieces represent millions of DNA fragments, and we're trying to reassemble them into the genomes of the microbes present in the environment. The first step in metagenomics is collecting an environmental sample, whether that's from seawater, from sediments, or any other sort of marine environment. Following that, we extract the DNA from all organisms in that sample and prepare it for sequencing, and then perform shotgun sequencing. a method that sequences random fragments of DNA, hence the name jigsaw puzzle. This approach captures the genetic diversity of the entire microbial community. After sequencing, we move on to the bioinformatics stage. This involves de novo assembly, where we piece together the short DNA fragments to reconstruct longer sequences, and metagenomic binning, which groups sequences based on common attributes that they may have. So this allows us to reconstruct genomes and obtain ecological and evolutionary insights, such as the previous example of updating the tree of life. We can think of metagenomics and reconstructing these genomes as getting a book as a bucket of seawater, a piece of soil, where each page is a microbial genome that is there. We pass that book through a paper shredder, or our DNA sequencer, which generates millions of tiny pieces. The next step is to assemble these pieces into longer fragments, and then to group these sequences together to try to reconstruct the pages of our book, our genomes. So our work tries to establish a model of global phytoplankton biogeography with the tools of metagenomics in hand, and to investigate how climate change may be influencing that distribution. So first we define this global model of phytoplankton biogeography. Second, we identify the unique taxonomical, the who, and functional, the what, characteristics of these biogeographical provinces, in addition of the environmental makeup that, that comprises them. Third, we develop models of how phytoplankton communities will shift under different climate change scenarios. To achieve these objectives, we compiled a global data set of over 2,000 metagenomes collected from major ocean regions, which are all these dots that you can see in the map there. This data set provides us with a vast pool of genetic information, enabling us to measure sequence-level distances between metagenomes and perform hierarchical clustering to group them into biogeographical provinces. We used a machine learning model to project the province areas from our sampling stations to the area of the global oceans, and applied a high-resolution coverage-based method to extract taxonomic and functional profiles from the metagenomes, leveraging a database of over 15,000 genomes reconstructed with the techniques I just covered. Finally, we use multivariate statistical analysis to examine how environmental, climatic, and biological factors differ between these provinces. So our first step was to measure the differences between our samples at the genomic levels. Samples displaying a varied degree of connectivity, represented by the edges that we see in this figure. We performed a clustering analysis that revealed 10 distinct biogeographic provinces of phytoplankton, shown here on this dendrogram, and also by the color of the dots shown on the map. This is interesting, but to understand how the biogeography of these organisms may shift under climate change, we want a more detailed spatial distribution going beyond only the sampling stations where they were collected. So we trained a machine learning model to predict the type of province at each sampling station based on the environmental parameters at each of those dots that you see on the map on the left. But then we fit that model to a global environmental data layer to see how provinces were distributed across the global oceans. And this is what we end up with. We have these 10 distinct biogeographic provinces of phytoplankton, each influenced by different environmental drivers. You can see that these provinces follow a latitudinal gradient, but they're also influenced by physical factors such as proximity to coastlines and influence from ocean currents. We have 3 categories of provinces: the tropical, with 3 provinces that you see in blue, light blue, and purple; the polar provinces in dark gray in the Arctic region and in light gray in the Antarctic region; and the temperate provinces shown in red, pink, green, and yellow. And you can also see the relationship in the clustering dendrogram that we created here. A unique finding from our study was that the Baltic Sea comprises a unique provinces which emerge as an outgroup in our clustering analysis. The phytoplankton communities here were distinct from those in other ocean regions, and this is likely due to the Baltic Sea's unique brackish environment. Temperature, oxygen, and nutrient concentration were the primary factors determining the composition of these provinces, but that different depending on the province. So here on the bottom right, you can see, for example, that in the Baltic Sea, salinity was the most important environmental factor to distinguish this province from the others. So just to clarify, the bars that we are seeing here are the importance of each of the environmental variables that we measured in order to determine and distinguish between those groups. And with this, we established the biology environment link. Our model was able to accurately predict the community composition, that is the province designation of a given geographical coordinate based on environmental data alone. And you can see that by this confusion matrix here, which basically shows the true label from our model the true label of the province compared by the predicted one from our model, and also the ROC curves, which measure model performance. One of the key findings was a polar shift in phytoplankton communities, consistent with patterns observed in larger marine organisms. And here, the colored dots are where we expect these distributions to change. So to conclude, we established a high-resolution model of global phytoplankton biogeography. We integrated metagenomic and oceanographic data, and that provided us with robust predictions of community structure. And establishing this biology environment link, we paved the way for the incorporation of microbial observations into Earth system models. With this, I'd very much like to thank my supervisors, my lab members, and the Royal Society of Victoria for listening to me tonight. Thank you very much.
Thank you so much for this inspiring presentation. So talking about the microorganisms and phytoplankton, I guess if you want to just come with one key message that how the diversity of these microorganisms helping us to predict the future of, the impact of the climate change. So from your experience, what would be?
Thank you for that fantastic question. So the truth is we know very, very little about these organisms. And that's why I introduced that technique of reconstructing the genomes by bypassing cultivation. That just has enabled us to obtain a series of insights into completely unknown organisms. And from this analysis, I didn't cover this in interest of time, but I have a series of bonus slides that go into this. We see that many organisms that are key to defining the spatial distribution of these provinces and these groups, they were largely unknown until very recently. So only by these techniques of bypassing cultivation could we know that one, that they exist, and two, what they could possibly do in terms of metabolism, so how they could affect these global biogeochemical cycles. And there is a body of work that recently came out just exploring this so-called microbial dark matter in the oceans, which is just microbes that are there and that have very great metabolic potential, but we really have no firm idea of what they're doing and how they're affecting the climate.
Sorry to ask another question. Can you predict what effect acidification of the ocean is going to have on those phytoplankton distribution?
Also great question. Acidification specifically affects more the concentration of carbonate, and that is a little bit more critical to organisms which are slightly larger than the ones that we're looking at here. Here we're focusing on phytoplankton, which are mostly prokaryotes, so bacteria, archaea, and very small eukaryotes, while ocean acidification would mostly affect larger microeukaryotes and other planktonic species, such as, microalgae and things like that. But for these specifically, these are the very, very tiny things. What dictates their distribution is mostly temperature, oxygen, nutrients, and salinity to an extent. So I would say that this sensitivity to ocean acidification is critical, but would be on a different, we call them different size fraction of planktonic organisms.
Thank you. It's fascinating. I was particularly fascinated by the map of your provinces. It's a remarkable agreement with large-scale ocean variations, including that big purple tongue that shows the El Nino, La Nina space there. I'm wondering if you could comment on how those results compared to your hypotheses when you started. Is that the sort of map you expected to get?
No, I wasn't sure what I was going to get. I was actually pleasantly surprised when I saw this strong correlation with oceanographic parameters and sort of classical models of the distribution of these oceanographic provinces. We do have a few of these models which are based solely on abiotic or environmental data. And it was very nice to see the correlation of that with the metagenomic data. So I think for me that really made it clear that link between the biology and the environment. So I thought it was very pleasant surprise, very striking to see. But as we start to untangle some of the subtleties of that distribution, we can kind of see the more complex and detailed interactions with the biological systems and individual microbial species and so on.
Oh, okay. So as Lyndon pointed out, like your map looked really nice, but phytoplankton have been around for a long time, and the Earth once looked very, very different. So I wondered if there might be any patterns associated with how the oceans used to be, with the oceans and the continents looking different.
That is absolutely fantastic. I would be fascinated to do that sort of work, sort of look into the past, I guess along the lines of Calla's talk. Currently for this work, we focused on doing a very detailed description of the taxonomic and functional characteristics of each of these provinces. So the work on relating that to past and future climates is still a little bit preliminary, but it's something that I would be thrilled to continue to work on in the future. I am really fascinated by this link between the oceanographic and the biological.
Thank you so much. Yeah. Would you like to get up and stretch and have a break? We're halfway through. Have a couple of minutes and stand up and stretch your legs, and we'll come back with our last 4 presentations. Don't leave the room, unless you
If everyone could rejoin us, take your seats, please, and we'll get back to it with our fifth speaker. Thank you.
Okay, so now we move to two presentations in the biomedical and health sciences. And the first one is from Diu Hashana Sakti and how do I say what's your last name? What's that? Okay. Very good. Lovely to meet you. You're at La Trobe. Your lead supervisor is Professor Michael Foley, and your presentation, the discovery of broad-spectrum single antibody therapy against malaria, toxoplasmosis, and babesiosis. I don't know that word either. Very good. Welcome.
Thank you. I'm Dimutu Angake. I'm a PhD candidate at La Trobe University. So today I'm going to present you part of my PhD journey where we discovered a small antibody-like molecule against malaria, toxoplasmosis, and the babesiosis. And all of these three diseases are caused by diverse parasites in one group called epicomplexans. In malaria, the disease is transmitted by Anopheles mosquitoes, and the parasites are infecting mainly our red blood cells and liver cells. Toxoplasmosis is transmitted by contaminated water and the food, and the parasites can infect our brain, heart, eyes, and muscles. Babesiosis is a primarily veterinary disease, but it can cause infections in humans. It transmitted by ticks. Parasites can infect our red blood cells. And when we talk about the disease burden, the malaria currently causing 240 million cases and more than 600,000 deaths in the worldwide. Currently, even though Australia is free of malaria, the global warming can make Australia vulnerable. In toxoplasmosis present in everywhere. In Australia, it's estimated 1 in every 3 people are exposed to this parasite. And babesiosis is a currently big concern in Northern American region and Eastern Europe. In Australia, we are quite safe, but the first case reported in 2012. So all of these 3 parasites, the common feature of all of these parasites are they have to infect human cells in order to multiply and cause the disease. And all of these 3 parasites, they have one common feature, which is in the invasion process, which involving 2 proteins to make the entry into the host cells, which is AMA1 and RON2 protein. So in invading parasite, what they are doing is they are injecting the RON2 protein into the host cells, let's say the red blood cells, and then the AMA1 protein goes and bind to it. And then the parasite will lock into the host cells, and then parasite can easily invade the cells. So because of that, the AMA1 has been widely researched as a potential vaccine candidate. However, it has been challenging because the surface of the AMA1 protein has changed between the parasites and the species. So because of that, even though it's more like the Australian finch birds, where I have more color variations, even the same bird, but more color variations. So because of that, even though we generate a vaccine against the one protein, it may be not effective to the other species or the strains. So in my PhD, what I aim to look at common and more protective regions of this protein by using small antibody library called iBodies. So iBodies basically inspired from shark antibodies. They are small, they have bigger binding loops. So my research group back in the day, they engineered this shark antibody to safely use in humans. So how I did it? So I'll bring back the finch analogy. So what I did was I screened the iBody library against purple color finch bird. And then after a few rounds, what I did was I introduced that antibodies into the green finch bird. So what I plan to do is at the end, I will see antibodies that bind to both finch birds as well as some other color variations. So I did the same thing with the AMA1 with 2 different molecules, and I finally found 12 different antibodies. As you can see, the greatest binding strength will show in red color, and the lowest binding strength will show in white color in this heat map. So as you can see, both WD33 and WD34 antibodies are binding to all the AMA1 variants that I have tested in Plasmodium falciparum, which is the deadliest malaria parasite in the world. So then what I did was I looked at whether these two antibodies can bind into other species, especially Plasmodium vivax, which is the second most common malaria species, and the mouse malaria as well. It found only WD34 can bind to both species. So then what I did was I looked at whether any of these antibodies can inhibit the binding of RON2, which is important for the parasite to invade the cells. So in this graph, as you can see, when I increase the WD34 concentration, you can see the RON2 binding decreases. That means WD34 have the ability to block the RON2 binding. With all this information, then I tested whether WD34 can inhibit the parasite in the red blood cells as well as the liver cell invasion. So I know this graph is so complex, but look at all the color variation lines. These are presenting the different parasite lines that we have tested in the lab. As you can see, when we increase the WD34 concentration, the parasite growth has gone down in the red blood cells. Likewise, I showed that the WD34 can inhibit the liver cell invasion as well. So we know that the WD34 binding all the AMA1 variants that we have tested, and it's blocking RON2 binding, as well as it's inhibiting the red blood cell invasion, as well as the liver cell invasion. So we want to know what's the mechanism. So in order to answer that question, we solved the structure of the AMA1 and WD34 complex by using X-ray crystallography. And then we looked at where it is binding. So as you can see, it's binding, it's the same area as the RON2. So when we analyzed that this area, it got clear that this area not only common in Plasmodium parasites, but also in the other related parasites called such as Toxoplasma and the Babesia. With that information, I tested whether WD34 can bind into the Toxoplasma. This is the microscope picture. The red color indicates the WD34 binding. As you can see, it's binding to the Toxoplasma parasite. Then I tested whether WD34 can inhibit the Toxoplasma parasite in the cultures. So as you can see, when I increase the antibody concentration, the parasite growth is slowing down. So I tested WD34 against the babesiosis. In here, what I did was I injected the WD34 into the mice, and then I challenged with the Babesia parasites. And then I looked at whether animals can handle the disease. As you can see, the blue and black color lines are indicating the control. We haven't injected anything, and the 21H5 is an unrelated antibody. And as you can see, the animal, the parasites can go up to higher level, but in WD34, when we injected WD34 animals, those mice can handle the disease quite well. So beyond WD34, is there any other approach that the antibody screening that we can do? And of course, it holds the promise against the other pathogens such as influenza. We know the influenza changes every year, so we have to get the flu shot every year. So this is one reason is because of the protein called hemagglutinin. Hemagglutinin is getting changed more frequently. Because of that, influenza are categorized into 18 different classes. So what we did was we took far apart HA1 hemagglutinin molecules, and we did the same strategy of antibody screening. And we found out that some I-bodies can bind to both HA hemagglutinin variants. At the moment, we are doing the experiments to see whether these I-bodies can identify the other hemagglutinin molecules. So the future of the WD34. So at the moment, we are doing a lot of preclinical experiments, and some of them are conducting at the moment, and some of them are we already planned. And we applied for the full patent application. And with all these results, hopefully we can start the human clinical trials soon. So I would, because this work is not an individual effort, we have collaborated with a lot of people, a lot of research groups in Australia, including my supervisors. I would like to thank you all. Thank you.
You have supervisors here, do you?
Yeah.
Yeah. Okay. Questions?
Oh my God, why? Thank you. That was a brilliant talk. I think I'll jump in first with a question of my own. What contributes to the variation that you see in AMA1? Is it purely protein sequence? Is it a degree of post-translational modifications? Is it, similar to hemagglutinin? Is there carbohydrates that are associated with it?
No, it's basically the amino acid sequence variations. We call it as a protein polymorphism. So it's basically from the parasite to parasite, the amino acid composition is getting changed.
And as a follow-up question to that, when you've looked at for example, a candidate H1 or a candidate H3 hemagglutinin, have you then looked at variants within that to see if you're getting consistent levels of blocking between, for example, yearly variants of hemagglutinin?
Yeah, so I mean, at the moment, we are in the screening phase. So this is the most preliminary data that I got. So I'm screening a lot. So yeah, at the moment, we got like around 9 different I-bodies that which is binding to HA1 and HA3. So I screened against the other HA molecules as well. So it looks like that some of them are, having a very broad spectrum binding activity. We still don't know whether it's actually binding to the head or the stem, that kind of details.
I-bodies are, and in terms of once you would give them to people or mice or anything, how well does it feed into the standard antibody-mediated responses, which is especially important if the parasite's not getting into cells?
Yeah. Thanks. So for the first question, yes, at the moment, one of our I-bodies are in clinical trials in phase. It's just going into the phase 2. So when we did the phase 1 clinical trials, we looked at the safety and the tolerability. And it looks like that there's no immune response against the molecules because it has been humanized. So we didn't see any immune reaction from the participants who are in the clinical trial. So this for the second question is, yeah. So these I-bodies, because we know that since it is small, the half-life is quite short. So because of that, we did the FC formatting when we are doing the animal experiments and the animal experiments. So when we are doing the FC formatting, we in the mouse experiments, we use the IgG1, which is having a very low effector function. And when we are going to the human experiments, we are actually mutating the residues, which causing the effector functions. So probably we can go with DAPA mutation, for example, or else recently NIH introduced another mutation called LS mutation, so which doesn't have any effector functions.
So I actually had a very similar question that my understanding of chemotherapy and toxicology testing is that you'd actually inject a concentration a couple of orders of magnitude greater than what you might use to be clinically effective. Is there any data on that?
Yeah. So the I-body that is in the clinical trials, it's against the pulmonary fibrosis. We call it AD214. So I think on top of my head, we went up to, I think 100 mg per kg. So it's still safe.
Question from you, and I think
Yeah, thank you. That's a wonderful presentation and really important research. So we know with parasites and hosts that it's an arms race, and parasites are very good at often winning that arms race. And I might have missed this in your talk, so I apologize if I did, but how well do the trials take into account variation, let's say within toxoplasmosis? I guess, you showed that graph that, the growth rate is dropping off, but it's not hitting zero.
Yeah.
So my question is, like, how well do we know about this ability with, other variants, if you like, of toxo?
Yeah.
How do you imagine this playing out? Like, do you imagine it being effective across pretty much everything, or do you think that there's going to be this arms race going on, and you may find that in different situations it's less effective?
Yeah. Yeah, that's a great question, because I didn't show the affinity data. So because I can clearly show that in the affinity data, because in the Plasmodium parasites, especially the Plasmodium falciparum, the affinity is somewhere between 1 to 10 nanomolar range. But if you go into Plasmodium vivax, it's going into 80 nanomolar. So in the Babesia and the Toxoplasma, when we tested, it's like around 500 to 800 nanomolar, which explainable, because even the area is a bit conserved. I think there are, residual contacts that, causing this. But the bright side is, because this is a good lead compound, so we can do affinity maturation, for example, and make it much more better and more tailored therapeutic.
That's all the time we have for questions.
Yeah, thank you.
Terrific. Really good. Our second presentation in biomedical and health sciences comes from Lisa. Here's Lisa. We met earlier. Miss Lisa Letzimitkel from the University of Melbourne. Her lead supervisor is Professor Misty Jenkins, who's Melbourne and La Trobe. Presentation on novel human FA3 specific CAR T cells eliminating adult and pediatric high-grade gliomas. This will be. I'll start from base level here. Thank you.
I've done a sneaky change of title, so to make it simpler. All right. Good evening, everyone. My name is Lisa, and I'd like to thank the organisers for the opportunity to talk today, and all the previous speakers for their beautiful presentations. So today I'm going to talk about my project in designing targeted cellular therapies to cure brain cancer in preclinical models. The diagnosis is glioblastoma. That is a sentence I hope you never have to hear. This is one of the most aggressive forms and fatal forms of brain cancer. And for patients with this diagnosis, the prognosis is dire. An average overall survival of only 12 to 15 months, despite current treatments. In young children, a type of brain tumor called diffuse intrinsic pontine glioma, or DIPG, is a truly insidious disease that grows in an area of the brain that is impossible to operate in. These primary school aged children are given less than 1 year to live. And as many of us can imagine, the brain controls much of our cognitive and motor functions and really controls a lot of who we are. For patients with brain cancer, the brain tumors can really rob them of this. Here I'm showing a beautiful microscopy image of a glioblastoma tumor in pink, growing within a living mouse brain. This image was captured by a talented postdoc in my lab, Dr. Matthias Muluzzani, and here he has labeled the tumor in pink and the blood vessels in yellow. And we can really see how this tumor infiltrates within the healthy tissue and grows intertwined. Now, standard of care is surgical resection followed by chemotherapy and/or radiation. And really, this protocol hasn't changed for the last 30 years. Through images like this, I hope we can appreciate how difficult it is for neurosurgeons to fully remove the tumor, remembering that they don't have this pink dye to help guide them. They're going in it much more blindly. And as many of us know far too well, the severe side effects of blunt, non-specific therapies, such as chemotherapy and radiation, mean that patients face toxic side effects. However, I'm here to tell you that we are living in a paradigm of personalized medicine, where we can tailor treatments to patients and their diseases. An example of this is a cellular therapy known as chimeric antigen receptor, or CAR T cell therapy. And this will be the focus of my talk today. Before I get into that, I'd like to take a step back and talk about our immune system, an incredible defense mechanism that is built to protect us from infection and cancer. Immune cells, such as the T cell, are designed to survey our body and seek and destroy pathogens and cancerous cells. And this occurs through a highly specific interaction between the receptor on the T cell and an antigen on a cancer cell. But of course, no system is perfect, and cancer cells can adapt and hide away from our immune system, a concept that we call immune evasion. However, what if we can actually modify our immune cells to regain their ability to seek out these cancer cells? And this really is the basis of CAR T cells. In this technology, what we can do is take a blood sample from a patient, isolate the immune T cells, and modify them to express a specific receptor, what we call the CAR. When these cells are reinfused back into the patient, they are directed to specifically kill the cancer cells, meaning that we are leaving our healthy tissue unharmed. A pivotal case in the CAR T cell field is this patient, Emily Whitehead, who was a child diagnosed with leukemia in 2010. In 2012, she was the first child to receive CAR T cell therapy, and now she is more than 10 years cancer-free. Now, the mission of our lab and many others across the world is to translate this success into brain cancer. And we want to do this by developing new and novel CAR T cell therapies for patients with brain cancer. In order to design these CARs, we must first understand what tumor antigens we are targeting. So we have collaborated with hospitals across Australia to obtain rare patient samples. And what we do is we meticulously analyze these samples to understand what antigens are found in these cancer cells. Now, I came along in my PhD and I mined this large data set, and I found a particular protein of interest. I found FA3 antigen was highly expressed in both adult and pediatric patients. When I delved further into the literature, I found that FA3 had been shown to have a role in the ability for the tumor to grow and survive, and specifically also had an expression that was found in these cancer cells and not in healthy cells. Now, there was already an antibody against this protein in development that had been shown to be safe and specific in humans. And what I did is I used some clever engineering and combined this with our immune cells to create what I call our FA3 CAR T cell therapy. Now, my work focuses on using preclinical models of two particular brain cancer subsets. What I mentioned before, the pediatric DIPG and the adult glioblastoma. We use preclinical mouse models to replicate what might happen in a patient. So what we can do is implant tumors directly into the brains of these mice to model how a tumor might grow in the brain. We can then treat these mice with our CAR T cells, similar to what would happen in a patient, and observe the effect over time. So, for example, in an untreated group, we would expect, so these are mice that are given the tumor and no treatment, we would expect that this tumor size increases steadily over time. If a therapy is effective, we would expect in the treatment group for the tumor size to increase initially, but then start to decrease over time as the treatment takes effect. So the first model I used was this pediatric DIPG model. And in my untreated group here, I'm showing a steady increase in that tumor size as expected. And this was promising to show that the implantation had worked. When I delivered the CAR T cell therapy in these mice, I saw that there was a steady decrease in the tumor size in 5 out of 7 mice. I'm showing these images here to show you the stark difference in the size of these tumors, with large tumors found in red signal and the small tumors in the blue signal. Importantly, you can see that the 5 mice in the middle there actually have no tumor at all. And this was absolutely amazing to see this, but I wanted to do more. I wanted to see if this particular therapy could be used in other models. So I moved into the adult GBM model, and strikingly, I saw an even better response. Here I'm showing 5 out of 5 mice showing a complete clearance of their tumor, and interestingly, a sustained tumor-free status. Now, the length of the time that these mice remained tumor-free got me thinking, what's actually happening here? Is it that the tumor cells have been completely eradicated, or is there something else that's keeping these tumors at bay? Now, I'm going to talk a little bit about something that we call immune memory, and it's one of the benefits of using immune cells. Basically, the concept of this is that a small population of these cells can remain in the body for a long time, similar to when you're given a vaccine. And then these cells can become reactivated if they see the same tumor antigen again. My hypothesis was that if these CAR T cells formed a memory population in these mice, then they should have an anti-cancer effect if they saw the tumor antigen. So to test this, I took those 5 mice that had cleared their tumors of their GBM tumor, and I injected tumor cells in the opposite side of the brain. Importantly, I did not give any further treatment as I wanted to test for this memory response. To cut a long story short, we were absolutely amazed to see that we had a memory response to this tumor implantation in all mice. And we showed that 4 out of 5 mice had a complete tumor clearance that lasted up to 130 days. That is more than 4 months, which is a long time for the lifespan of a mouse. Now, this proves that there was, in fact, a memory population that remained in these mice that could become protective in preventing outgrowth of these implanted tumors. So in summary, I hope I've shown you that this novel FA3 CAR T-cell treatment was effective in adult and pediatric brain cancers. I've shown that they have been completely curative in preclinical models. And most importantly, I've shown that they have immune memory that could potentially prevent tumor relapses in patients. We were really excited to publish this work recently in the Journal for Immunotherapy of Cancer in August earlier this year, and also had this story picked up by a few news outlets across Australia and international, including front page of the Herald Sun. So our next big goal is to translate this success into the clinic, and we are actively looking at performing a first-in-human clinical trial here in Melbourne, which will be a fantastic opportunity for our brain cancer community. Overall, I'm extremely proud of this work, and I hope that I can have shown you the implications of this discovery and how this could be potentially life-changing for patients with brain cancers and their families. I'd like to conclude by acknowledging everyone on my team that has been a very important part of this work, in particular my 2 supervisors, Misty and Ryan, for all their support, as well as all our funding bodies that make this research possible. Thank you.
Lisa, that's remarkable. You've convinced at least one person who knew nothing about it. You've delivered that, and I understand that very, very, very well. Ewan.
That's such brilliant research. Congratulations. So important. What's happening with those mice that didn't do what we wanted them to do?
Good question. It's something we're still investigating, but what I hypothesize is there could be things such as what we call antigen loss. So the tumors might regrow, but they might not be expressing that antigen. And that's a very well-known mechanism and what ultimately happens in a lot of patients. And it's very much a possibility here. To address that, I think the overall field is looking at different ways of targeting these tumors potentially with combination. So either CAR T cells plus, radiation chemotherapy, which would probably be the first. I don't want to speculate too much, but you can certainly combine. And we've actually got work in our lab that is looking at multi-targeting as well. So using CAR T cells that target multiple antigens, so that you're kind of hitting the tumors really hard right at the beginning. So not to give them a chance to come back. Thank you
for that presentation. Thanks. Based on the second question, just off that one, for those assuming this goes to a clinical trial and let's just go one further to humans, how would you then screen for the patients who would benefit from this so that they're getting that personalized medicine? Or is there any risk in terms of toxicity effects if they were to get this treatment and then they, didn't respond to it?
Yeah, that's a really good question. I think that's, to be honest, something that the field's still tackling. So, for example, I think for some of the clinical trials that have already been run, a key potential challenge is patient selection. So, for example, they may be given a targeted therapy, but maybe that patient wasn't the right choice. And maybe they didn't express that antigen of choice enough to have that sort of level. Obviously, brain cancers are difficult because they require a biopsy or surgical resection, which could have sampling biases. I guess it would also depend on at what point the treatment is given. So, for example, there's been some evidence to show if you give the CAR T-cell treatment before surgical resection versus after, or, after radiation chemotherapy can potentially affect the efficacy of it. So I think that's sort of the field is still playing around with the timing of when this treatment should be given. But certainly I think definitely a screening of the tumor and what antigens they might express is going to be key in delivering that very tailored and personalized medicine.
Thank you. Very nicely presented too.
Thank you.
You've done more than 5 mice, I presume, have you?
Yes, definitely. Yeah.
This is just a sample.
Yes.
I was wondering how much detail did you look at the brains after you'd cleared the tumor? Did you take histological sections to look at what they were like?
Yes. Yeah. So we've predominantly we tend to fix and do histology on them. I've started to look a little bit, unfortunately, I've had a little bit of technical issues working up a particular antibody, but I've shown that, for example, I can see infiltration of these T cells into the brain and even the different types. So there's different types of T cells. So we're just starting to look at that now and looking at more of the mechanism of what's happening within the actual brain. I kind of touched on the memory response that I'm seeing there, and I've done a few preliminary experiments to look at the types of memory cells as well, because we know that there are different subsets of memory cells, and there's a lot of kind of discussion in the field at the moment about whether or not a particular type of subset of memory cells would be more favorable for patients. But yeah, that's sort of up in the air still at the moment. But yeah, it's something I'm really interested in looking at.
I think he has questions to say.
Love the presentation, and I should point out that as a family that's heard the words, you got glioblastoma, I can relate to the impact of what your work is. I guess my question is, as a scientist who sees such positive results coming from your research, what frustrates you the most when you see these sort of results coming out? And I guess the second question is, what are you afraid of? What not working next?
So the first question was, what frustrates me? I could probably talk on behalf of my supervisor. So Misty's so excited about this work, as we all are, and she's working so hard to get this into a clinical trial. But it is a whole nother feat and a whole logistical hell, I think. There's obviously funding is going to be a massive challenge, but also the logistics. And obviously this is a cell therapy, so it's not quite as simple as like our traditional drugs. And I think maybe Australia's still just learning how to do this. I know in the blood space, there's definitely been a lot of work being done there. So yeah, I think I would say for me, and also just talking to, we have a lot of consumers, we talk to patients, and I think they see this and they think, well, how quickly can we get this into patients, and why can't that be sped up? Unfortunately, I think that's a whole nother world above us, and unfortunately, it is this length of time that becomes really frustrating. I can't remember what your second question was. Yeah. I guess the next big thing is, does it work in humans? And the only way we're going to know that is to put it, to trial. I think there's a whole host, obviously, humans are extremely complicated diseases, and we use these models to the best of our ability, but no model is going to recapitulate a human. And I think there's always that fear that that's not going to translate. But for me, this is like, I'm very much a bench scientist, so this is the closest that I've ever gone to touching anything that goes into a human. So it's a really exciting time, I think.
Certainly is exciting. Now, our final two presentations for the evening in biological sciences. Eliza Thompson. Where's Eliza? Come up, Eliza. Say hello. Eliza's at the University of Melbourne. Her lead supervisor is Associate Professor Luke Kelly, and she's presenting tonight on promoting bird diversity in plantation forests of Western Victoria. They probably need it.
Thank you. Thank you everyone for coming to my presentation tonight on promoting bird diversity in forest plantations. I'd first like to acknowledge the Wurundjeri and Gadigal Mara people, the traditional owners on which this work took place, and pay my respects to their elders past, present and emerging. I'd also like to acknowledge the wide range of people that helped contribute to the success of this project over the past 3 years. So plantations. Plantation are areas where trees are grown. They're grown to a particular size and height, after which they're harvested for wood and pulp products. Besides plantations, there's also native forests that are logged for these products. However, recently in Victoria, there's been a ban on native logging, and this has put more pressure on plantations to continue to provide these products. So therefore, there's kind of a knowledge gap on finding ways to sustainably manage plantations, not only for their longevity, but also for conservation for the wildlife species that exist and within and around these areas. So my thesis aimed to understand ways to improve bird diversity and the biodiversity value of plantations. So I focused on the Green Triangle, which is out in Western Victoria. And within this region, there's a large amount of blue gum plantation. So blue gum plantations are not native to the region, but they're native to Tasmania. The Green Triangle is also home to a range of bird species. So more than 200 bird species have been observed here, and they come from a range of different groups. So there's species that prefer forests, so they need treed structures for their foraging and their nesting. There's also some species that require less trees, so they prefer more open habitat. There's variation in diet, such as those that eat insects or small little brown birds. And there's also variation in nesting types, such as those that rely on large old trees that have nesting hollows in them. So my thesis was broken into 3 main questions. Firstly, how much habitat is enough for birds in these forestry landscapes? What should this habitat look like to conserve individual birds? And how can we encourage land managers to encourage biodiversity? So what are the benefits they can also gain? So the first question, how much habitat is enough? So for this question, I wanted to determine how birds respond to native vegetation that still exists across these forestry landscapes. So despite planting trees, there's still native vegetation that's embedded and surrounding these areas. And I also wanted to determine how different bird groups differ in their relationship with native vegetation. And from these, directly go back to managers and tell them how much native vegetation that they should save for these area-based targets for bird conservation. So the design of my study looked like this figure. So you can see here the scattered amounts of blue gum plantation and native vegetation. You can see the black circles there represent the 36 study landscapes that I observed birds at, with the 4 circles at the bottom demonstrating the variation in native vegetation within these landscapes. So on the left-hand side, you have 0% of native vegetation all the way up to 72%. Those purple circles represent the bird survey sites that I assessed over a 2-year period. And from all the data that I collected with my field volunteers, we analysed 4 bird groups. So habitat preferences, variation in diet, foraging location, and nesting. And I'll just take you through one of those group results. So on the graph here, you can see along the x-axis or the horizontal line, you can see that the amount of native remnant vegetation. And on the vertical axis, we can see the number of bird species or species richness. So each circle there represents a different study landscape. And you can see for all species and forest species, we have a rapid incline in the number of species to about 10%, and then we kind of get a plateau. For open country species, we don't see these species responding to increasing amount of native vegetation, and we can see that as just a flat line. So from these modeled responses, we can draw area-based targets. And I looked at trying to attract 90% of the birds we observed. So you can see that the forest group there is the most sensitive and requires 17% of the landscape to be composed of native vegetation. So if we know that birds need native vegetation, what should this habitat look like? So for this question to be answered, instead of looking at bird groups, I focused in on individual species. So again, I looked at the amount of native vegetation. I also looked at how this native vegetation was arranged, whether it was clumped or whether it was dispersed, which affects birds' ability to move throughout a landscape. And I also looked at the diversity of different land uses. So as well as native vegetation within the landscape, there's plantation, there's farmland, there's different water sources as well. So I was able to analyze 27 of the species of the 107 I observed. And I was looking at both the presence and abundance of these birds. So if they were there and how many were there. And I analyzed these in relation to with the three variables, the amount, the configuration, and the diversity. So I found that 5 species strongly responded to the amount of remnant vegetation. For example, the white-throated tree creeper. So you can see on this figure here, it increases in its presence at around 10%. And then you get these white-throated tree creepers occurring in the landscape because of this unique structure in the remnant vegetation, which is this rough bark eucalypt trees. So they use these trees to forage in, and in blue gum plantations, they have smooth bark, so you don't have these foraging opportunities. In terms of configuration or how connected these native vegetation patches are, I found 6 species responded to this element. For example, the white-browed scrub wren. So this is a small bird that relies on understory or bushes in the lower area of the vegetation structure to forage and nest within. So you can see in the figure that as you move from left to right, you get more landscapes that have well-connected patches. In terms of landscape diversity or the number of land uses within a landscape, I found 2 species responding to this variable. For example, the white-faced heron. So the white-faced heron is a water bird, so it's likely responding to the emergence of water bodies as these landscapes become more diverse. So if we know that birds prefer native vegetation and we can understand how it should look like, how can we convince land managers to promote conservation in these working lands? So one way we can do this is through insect attack. So plantations are really vulnerable to insect attack because they're mostly monocultures and they have really tight spacing between trees. So this is often managed with insecticide, but that can be harmful to the environment and it also costs a lot. An alternative way is to retain native vegetation, which can indirectly attack these insect predators and decrease the amount of insecticide that we apply. One of the most damaging insects in the blue gum plantations is a species known as the autumn gum moth. So it's most damaging in its caterpillar stage or its larval stage, where it skeletonizes or strips the leaves bare of young blue gum plantations. So for this question, I worked with forest health managers who assess these areas for different insects to analyze the presence of this autumn gum moth and the severity of its damage. And I wanted to see if the distance to different size patches of native vegetation as well as birds could decrease this attack. So I didn't find anything for the birds, but I did find something for the native vegetation. So on these figures here, if you're further away from that vertical grey dashed line, we're going to have a strong response. So I found that the distance to the nearest patch of native vegetation that was at least 1 hectare in size, so that's 100 meters by 100 meters, was important for decreasing both the presence of the autumn gum moth as well as its severity. So you should make plantations close to native vegetation to decrease this insect attack. So my thesis had 4 major findings. So the first was that area-based targets can be set for bird groups, and this will help forest managers help achieve nature-positive objectives. I was able to pinpoint the native vegetation needs of individual bird species in terms of the amount required, the configuration or connectiveness of patch and land use types. I discovered that size and proximity to native vegetation will help control insect pests, and this can benefit land managers directly. And that biodiversity does exist within plantations that can benefit both people and nature. Thank you.
Really nice piece of work, Eliza. Let's have some questions from our judges first. Ewan. And then Ivan's got a question down here, Scott, when you're ready.
Terrific work, Eliza. Well done. So in terms of convincing, a producer to maintain native vegetation, could you put an economic value on these birds in terms of their pest reduction, capabilities? And that way, encourage people to move away from insecticides by saying, okay, if you have this much native vegetation, this close to your plantation, this is the financial benefit that these birds are providing to you?
So I actually got asked a similar question by land managers the other week, and I don't have an answer to it. I didn't look at the economic feasibility of it, but they were very interested in it. And currently they're trying to set up kind of this native vegetation quality monitoring program to try and really enforce the kind of results that have come from my PhD. In terms of monetary, I don't have an answer though. It's a very interesting question. Yep. Thanks.
Thank you. Really interesting. I have two questions that are very different. If I understand it, you didn't get a correlation with a bird type. Do you therefore have any explanation for what is going on in the native forest, which impacts the health of the bluegum plantation? And the second one is site selection in this sort of thing is crucial because the topology of your shapes can be critical with your outcomes. And I was wondering if you could just talk to that.
The first question. So other sources of insect predators within native vegetation could be bats or other invertebrates. So the autumn gum moth is parasitized by wasps. So that could be a source of them. You said topology. What do you mean by topology?
Size and shape and relative shape of the areas of the forests, the native forests and all the plantations and the open areas, particularly the length versus width, if it's approximately rectangular, let's say, or if there are holes in these areas, can be crucial to impacting the outcomes of your data.
So the configuration metric kind of gets at that in terms of like isolation and how they're connected. I didn't look specifically at shape just because it's correlated with a bunch of other variables. But yeah, definitely those sorts of things would likely to have an influence. I just didn't look at them directly. Yeah.
Another question or from general audience? Yep.
You mentioned the effect of diversity. In that area, you've got the Glenelg River and the Rocklands Reservoir, large bodies of water. How did you control for proximity to those waterways, and did you see an effect?
Yeah, so with the waterways kind of land use kind of type, I looked only within the landscapes that I was directly surveying the birds. But definitely with the proximity to water bodies, you'd probably likely see more relationship with the water birds. Other than that, there was kind of flooding going on in the area as well. So I think that's probably likely influencing the birds. A lot of the rows in between the trees was kind of like rivers. So I had to do a lot of jumping in that aspect. But I reckon the water bodies and proximity might be some sort of relationship there that I could go have an explore, I reckon.
Another question? No? Thank you, Eliza.
Thank you.
That's terrific. Well done. Been sitting all night. Darcy Watchon, can you come up and introduce yourself? Where's Darcy? Been sitting watching all these wonderful presentations all night and he's lucky last. Darcy's at Deakin University. His lead supervisor is Professor Don Driscoll, and his work is on advancing mammal conservation in the face of fire and invasive predators. Critical stuff. Welcome, Darcy.
Save the worst to last, huh? It's not the first time. Yes, hello everyone. My name is Darcy and I'm a PhD candidate from Deakin Uni. And yeah, tonight I'm talking about advancing mammal conservation in the face of fire and invasive predators. So first of all, I would like to give you the essential but undeniably miserable background context for my project. So miserableness is kind of hard to escape in conservation ecology. I've been learning over the years. Now, Australia has the worst modern mammal extinction rate in the world, boasting 35% of all mammal extinctions over the sort of past 500 years or so. That represents about 30 species that we've lost. Now, the invasive red cat, red fox and feral cat are two major contributors to this miserable record. Each year in Australia, they kill an estimated 1.4 billion native animals, and they've contributed to 28 of those 30 extinctions. Now, fire is a really important ecological disturbance across most of the country. However, fire regimes, and that simply means the timing, location, and severity of fire events, have changed a lot since European invasion for a whole host of reasons. And now inappropriate fire regimes threaten about 88% of Australia's land mammals. So there's growing concern that the threats of fire and invasive predators might actually be interacting with one another. And this might be leading to even worse outcomes for some of Australia's native mammals. And the potential mechanism behind this interaction is fairly straightforward. So feral cats and foxes are really terrific hunters, but they can find it more difficult to detect and catch prey in really complex environments, like dense vegetation. And fire, of course, consumes that understory vegetation and simplifies the habitat. And so cat and fox activity can increase then in burnt landscapes, likely because their hunting success is improved in the simplified habitat. It's easier for them to see and catch prey. And the strongest evidence for this interaction comes from a series of studies from tropical northern Australia about a decade ago. And since then, there's been several studies from different ecosystems across the country testing this idea, but they've kind of found varying results. So it's unclear at the moment whether increased cat and fox activity in response to fire is a general phenomenon that kind of happens more or less after every fire, or whether the responses are more context specific and not really generalizable. So the first of my two PhD aims was to better understand how cats and foxes respond to fire, because this is, of course, critical for developing effective management strategies. Now, as ever, a good way to better understand a phenomenon is to review the literature and do some meta-analysis. So that's what we did. And we looked at and analyzed all of the studies that have looked at the changes in cat and fox activity in response to fire across the country. Now, the key finding from this study was that there was no widespread evidence of cats and foxes consistently increasing their activity in response to fire. However, when increases did occur, they were more likely to happen shortly after fire. So, for instance, the probability of detecting cat activity or increased cat activity was 41% at 0 months post-fire, and this decreased down to 10% at 100 months post-fire. For foxes, the probability dropped from 53% down to 10%. Just get my mouse here. So further studies are needed to help grow this knowledge base, particularly those that begin sampling shortly after fire, ideally within a few days or a week or two, and particularly in temperate forest ecosystems, because there's still a real dearth of data from these regions. Okay, so that brings me to paper number 2, where we experimentally tested how cat and fox activity changed in response to prescribed fire in a temperate ecosystem. So the background image here is my lovely study region, the Eastern Otway Ranges just behind Anglesea and Aries Inlet. And here we set up a camera trap grid comprising 30 camera traps ahead of a planned burn all the way back in 2019. Now, I realize that some of you may not know what camera traps are, but they're these motion sensor camera traps, motion sensor traps that we use to survey animal activity, and they can be left in situ for several weeks or sometimes several months. And I use tuna oil as a lure to bring nearby animals into the frame of the camera to increase my ability to detect them. We surveyed my sites at 6 months and 2 months before the fire, and then again at 2 weeks, 3 months, and 6 months after the fire. And the key finding from this paper was that we found no response of cats to the prescribed fire at all. Meanwhile, fox activity was higher after the fire, but this was across both the burnt and the unburnt sites. So due to the proximity of our control and treatment sites, I'm not actually sure if it was the fire that drove this change. It could have been another mechanism like potentially juvenile foxes, which disperse at this time of year. Unfortunately, there's a little bit of uncertainty surrounding that result. Now, whilst this experiment provides further evidence that cats and foxes don't always increase in response to fire, which is valuable, we do know that this interaction does happen, and land managers need effective management options to reduce the impacts of cats and foxes after fire. And the most common approach that land managers use is lethal control, like trapping and poison baiting. But there are a whole host of restrictions around when and where this can be done, especially in Victoria. And successful outcomes can be difficult to achieve in open environments where there's continual migration of animals into the area that you're trying to manage. So one potential option that's been gaining quite a lot of interest in recent years is to deploy artificial refuges for ground-dwelling animals immediately after a fire. And so the idea here is that they could provide shelter from predators and improve the persistence of small animals until the vegetation regrows. Now, everyone's probably familiar with the concept of nest boxes for bats and birds and possums. This is a broadly similar concept, except it's for ground-dwelling animals. So the second aim of my PhD was to test the efficacy of an artificial refuge design for improving mammal persistence after fire. To address this, we initially conducted 2 reviews on artificial refuges and looked at why and how they've been used all around the world to learn more about their effectiveness and their shortcomings. And the key takeaway from this research was that only 39% of artificial refuge studies used experimental controls and less than 10 used a BACI design or before-after control impact design. So as a consequence, very few studies can actually confidently determine the overall effect that they're having on their target species and populations. And so this is really important because the use of artificial refuges is a strategy that really readily garners a lot of positive media attention because it's sort of a direct and tangible action that you can take in time of a crisis. And it can also really engage the community as well. But in many instances, it's still unclear whether artificial refuges are actually effective or they're just a well-intentioned but sort of ultimately ineffective action that kind of wastes a lot of time and money. And some refuges can even have a detrimental impact on the target species in what we call an ecological trap. So I wanted to learn from the findings of these reviews and make sure that I gained really robust insights into the efficacy of my artificial refuge to sort of best inform land managers. So to do this, I undertook 3 experiments. The first 2 looked at the behavioral responses of native fauna in terms of activity patterns to the refuges after fire. Now, the background image I used for these slides is a photo of one of my refuges. They were 50 meters long, are made from chicken wire and covered in shade cloth. And I built 5 of them at each one of my sites, and they kind of were parallel with each other, about 10 or 15 meters apart. And there were no larger openings in these refuges, so only animals that could fit through the 5-centimeter gaps in the wire could enter, and they could enter and exit from any point, so their behavior, in theory, didn't become predictable to predators. And to put it mildly, they were absolutely hell to install, but I had a really great team of volunteers helping me out. And so we did a control impact study in the Otway Ranges, as well as on Kangaroo Island and in the Simpson Desert. And we built a total of 76 of these bad boys across these 3 sites, which is over 3.5 kilometers of chicken wire. And we found that activity was much higher inside the refuges for a breadth of species, particularly the painted button quail, like this cute little family having a stomp inside one. But also for superb fairy wrens, scrub wrens and heath wrens, and the small skinks. In contrast, small mammals showed mixed responses, with about 2/3 small mammal species showing no response compared to the controls. However, the Kangaroo Island dunnart and the bush rat both had positive responses, and that was really great because the refuges were built on Kangaroo Island specifically for the dunnart, which is a critically endangered animal that had most of its range obliterated in the fires. So that was a really good outcome. Now, animals also spent more time per visit inside the refuges. So small mammals spent up to an average of 43 seconds in the refuges compared to 8 seconds at the control sites. For birds, this is 20 seconds compared to 13 seconds. And small skinks doubled their time inside the refuges, 2 seconds to 1 second. Now, so taken together, these results suggest that the refuges are reducing the perceived risk of predation for small fauna, which is really great. But to understand if these trends in activity based data actually translate to improved population persistence, we need studies that test population metrics like survival or abundance or what have you. And so that's what I did in my final study, where I conducted another experiment using prescribed fire, again in the Otway Ranges. And this little guy here is an agile antechinus, some of you may be familiar with. In my opinion, I think these are the best small mammals in the Victoria. And if anyone wants to argue about that, bring it on. So I had 3 treatments, sites which remained unburnt throughout, burnt sites without artificial refuges, and then burnt sites with artificial refuges. And I surveyed small mammals across these sites over 12 months, twice before the fire and again 3 times after the fire. And we wanted to know how the refuges influence the abundance of 2 of the most common species at my sites, bush rats and the agile antechinus, as well as overall small mammal species diversity. What did I find? Well, unfortunately, no effect of the artificial refuges, alas. So despite my previous experiments, which show small mammals will spend more time per visit inside the refuges, and some species like the bush rat, really favored them, these findings are suggesting that the refuges don't actually improve the population persistence, which is kind of the key metric. And so at this point, I don't believe that we should sort of scale up the application of this management technique. However, large-scale field experiments like this are inherently context dependent and exceedingly difficult to control. That's kind of the beauty and the curse of ecology. And this is because there's a whole host of variables like fire size and fire severity, prey abundance and activity, prey population dynamics, and other variables will no doubt vary between my study and say another study that's undertaken in the forests of New South Wales in a completely different forest type, for example. So I'm still encouraging researchers, to undertake further experiments with artificial refuges after fire, including with alternative refuge designs and following severe fire when there's less vegetation remaining in the system. And yeah, that is it. I'd like to give a big thank you to my amazing team of supervisors, the many external collaborators that I worked with, also the many generous funders, and of course my amazing team of volunteers and my study animals. Thank you very much, guys.
So just the beginning. Watch the space. Exactly. Now, questions from our judges. Kat. Where are you? There you go. Yeah, we're waiting here. It's okay.
Great presentation. Your result was sort of like, there's not as much change for the small mammals, but I wonder, what about predation? So this is a 2-part question. How well can the predators sense that animals are within the refuges? And if they can sense them, is there a difference in their behavior? Because you said you didn't want them to be able to recognize patterns.
Yeah, good questions. I can't really answer the first one. It's really hard to measure. We built the refuges with that in mind. So the purpose of the shade cloth was sort of in part to obscure prey from predators visually, because the shade cloth pretty much went all the way down to the ground. But yeah, whether or not predators could still detect animals using the refuges, I don't know. You could imagine that, if there were hundreds of animals pumping through each refuge, then that might attract, cats and foxes and birds and other things as well. We didn't detect increased activity at the refuges from cats and foxes, which I think kind of speaks to your second question. So, but it is possible and something that should be monitored moving forward with anybody doing other research on this.
Thank you so much for that. Fascinating. So many questions. I'm going to stick to one, and that is, we know, for example, that foxes have co-evolved with things like blackberries, which are obviously also an invasive species. And that got me thinking, because they are one of the few species that can move through other invasive plant species. And so there's that co-evolution. To what extent could the absence of some of these effects be because there's a co-evolution of these mammals with fire in the Australian landscape, so that actually, you're trying to do the right thing, but actually there's other things we're not seeing that they're able to tackle by themselves?
I think I understand the question.
So sorry, yeah, that was, to what extent are they able, to what extent might this be a natural behavior of dealing with disturbance in the landscape? Much like foxes can move through blackberries to invasive species, which our native mammals can't, for example, which makes it so devious when you have blackberries and fox populations together, for example. The opposite of that.
So cats and foxes are both amazing generalists and really behaviorally flexible. There's data from elsewhere in the world, particularly in the Mediterranean, that show foxes, they do the same thing, right? So they respond to fire, they increase their activity. And the difference there is that in regions where foxes and cats are native, the prey are better able to recognize the cues of those predators and respond and hide and survive. Whereas in these systems, they're a little bit more naive. So the small animals themselves are typically really good at surviving the fire, but they're just more naive to the presence of cats and foxes, who are such fantastic hunters, and they're just more able to take advantage of them. Yeah, hopefully that gets.
Great stuff, Darcy. So I guess the question is, what would you advise managers? So, you know, as you said, there's a lot of effort going into these artificial shelters for good reason, but they're not maybe as successful as we'd like them to be, at least as much of the time as we would like that to happen. And then there's a scalability issue. Like, you just can't put these things across huge scales, some of the landscapes that we're dealing with. So what's your recommendation? Like, you know, we've got problems with cats and foxes. We know that. We've got problems with fire. There's some evidence that fire sometimes affects them, not always. Like, what's the best option at the moment from what you understand?
Well, with respect to the artificial refuges in particular,
Conserving biodiversity.
well,
not everything.
Yeah.
It's too hard. But
well, I'll start with the artificial refuges. I think they would have the most applicability for. I mean, maybe not necessarily mammals, because they do have relatively large home ranges compared to other small fauna, but you know, endangered species that have really restricted distributions, much like the kangaroo island dunnart, I think we can have a high output of money and effort, and to, you know, really essentially save a species from going extinct. So it's a high effort. Where high effort is warranted, then perhaps this type of thing, if it is effective, may be most suitable. In terms of other approaches for managing cats and foxes after fire, I mean, yeah, I really don't know. That's a good question. No, yeah. Who knows? Ask me again in 15 years. Thanks, Ewan.
I think question time's up. Is that right, Mike? I think we're done. Okay. Darcy, thank you very much. Well done. Yeah. And thank you. Can I ask you to put your hands together for all of our 8 presenters? That's the final presentation. I think we've seen an extraordinary level of great science presented this evening. Now, what happens next? You all get to go downstairs for some refreshments, except our judges don't. Judges get to retire to the Cudmore Library to consider what they've seen and have a little bit of a discussion. But for everybody, please come downstairs to the Burke and Wills room for some food and drink that awaits you. And we'll actually have our announcements downstairs. So we'll get all the way back up here. We'll do that downstairs. But terrific presentations.
To the YouTubers. Oh, sorry. Just a quick word to the YouTubers who are watching. That's all right, Rob. We're just going to finish up the feed now. I'm afraid you're going to have to wait till tomorrow to know who the winners and the second prize winners are. But we'll be making announcements via our website and social media tomorrow. So tune in then. Thank you for joining us tonight.